Hello everyone and welcome back. So this time we're looking at a different type of composite member, and this is going to be an indeterminate section that has members that are attached end to end. So our composite shafts shown consist of a stainless steel tube and a brass tube. They're connected at flange B and they're securely attached to rigid supports, so no slip at A and C. The stainless steel tube has an outer diameter of 2.25 inches, but it's hollow, and it's got a wall thickness of 0.25 inches. And there's lots of other things. And the brass tube is also hollow, has an outer diameter of 3.5 inches and a wall thickness of 0.219 inches. So with all that information, what do we want to find out? What we want to know is if we apply a concentrated torque of 42 kip-inch, what the maximum shear stress would be in tubes 1 and 2, and the rotation angle of point B relative to support A would be. So, follow the steps from our previous group problem and see if you can do it. I'll let you pause and try it out, then come back and we'll do it together. So 3, 2, 1, and let's continue. So first off, as almost always, we do the section properties. We calculate our polar moment of inertia, and we get it's going to be 1.59 inches to the fourth and 6.102 inches to the fourth. This is for the brass. This is for aluminum, I believe. Yes, was aluminum, brass, and stainless steel for that one. Then we write our equilibrium equations, which we can't solve yet because we've got two unknowns. We only have one equation. So we have to look at our geometry to figure out what's going on here. And what we should realize is that the angle of twist for section 1 and the angle of twist for section 2 have to be the same at point B. Because one's going to twist in a positive direction, and one's going to twist in the negative direction to go back to 0, because it starts at 0 and it ends at 0 because these are rigid supports. So when we add those two angles of twist together, well, they have to be equal to 0. So now let's develop our torque-twist relationships. We know everything in here except for the torque. And we also know that when we add these two together, they're going to equal 0. So one is going to be equal to the negative of the other. And so we can develop our compatibility equations. Now, with our original equation of equilibrium, we have two equations, two unknowns, and we can solve. Now, if you want to, you can do what it normally does in these problems, which is solve for T1 in terms of T2 and get it all like this. You can also just plug in all your numbers. I mean, there's lots of different ways you could do this. If you want to use a matrix, you can do that. I do find this method to be very helpful. It's just there's also the chance of having some horrible calculator error if you're not careful. So be very careful. Double check yourself. Make sure you don't make that mistake. Now, using that, I can plug it all back into my original equation of equilibrium. I solve for the torque 2, and then solve for torque 1. Now, I know what torque 2 are, I know what torque 1 is, and using my elastic torsion formula, I can calculate the maximum shear stress, because that's simply equal to the torque times the radius over the polar moment of inertia. So I do that for stainless steel, and I do that for aluminum. One has a shear stress of 6.69 KSI, another one has a shear stress of 9.32 KSI. I said stainless steel and aluminum, stainless steel and brass. In this case, the stainless steel actually had less stress because it was hollow too. It had a fairly comparable polar moment of inertia. Now we have to figure out what the rotation angle of B relative to support A is. Well, we know that section 1 is going to be equal to the rotation angle of B with respect to A. And since we're going to say that A is equal to 0 because it's held at a joint that's restrained from rotating, well, then my rotation angle in the first section will simply be equal to rotation angle of B. And so that would come out to be 0.1903 radians. Okay. So that's it for this time. Thank you so very much for your attention. Thank you for your hard work. If you struggle with any of those steps, make sure you go back through and you can pause and take a longer time. I know you writing down the numbers takes a lot longer than me talking about them. So have an absolutely wonderful day. I'll see you all later, okay? Bye-bye.